longitudinal wave also. I forgot to explain that longitudinal wave. See, transverse wave very clearly, we can mark the displacement. Okay, particles, yesterday we have seen, this is time. Okay, see particles, this first source keep moving up and down, seconds also moving up and down. So from mean position, each particle making simple harmonic motion to and fro, up and down, perpendicular to the propagation of the wave. Wave is moving from here to here, but particles are vibrating perpendicular. And we are getting a pattern like this. Yesterday we have discussed about it. Like this, isn't it? Let it be a little more. Like this it goes. Now, this is displacement, this is time. This is for transverse wave. But longitudinal wave means, I told you, in air, sound waves, example. It gets, see, you actually air is uniformly distributed everywhere, like this. Just draw this diagram. Uniformly distributed. Suppose when I speak, vocal cord just compress and pushing the air. So that get compressed. So this region, for example, get compressed. This is called compressed region. Their density of air will increase. But immediately that will expand because they are vibrating. Then what happened? This compression will go to rarefactions. Rarefaction means, see, they are far apart. They go apart. Again, they come to compression. You see, this is rarefactions. This is again compression. This is again rarefaction. It goes far apart. So if you draw a graph for longitudinal wave, we cannot mark displacement because displacement is in the same direction of propagation. So there what we use, we mark density. See, density we mark. Here density, you can see density increases because air get maximum compressed. Then density, draw the diagram.
Decreases.
Here density become normal again. Here density decreases because their particles are going apart.
Sir, what is the heading?
Longitudinal waves. Longitudinal waves. Okay.
So should we draw both of these graphs?
Yes. This is first one transverse wave. Second one just variation in air with the longitudinal wave. Then graph, corresponding graph. See. So here what happens? This go to maximum density, this region. Then come to normal here. It will come to a normal value. Here it is rarefied. Okay, rarefied means they are going bit apart. Here it is compressed. It is almost far apart like this. See, far apart. Here also same way they are little apart. This region compressed, this is little apart. Compression, rarefaction. So here it is rarefied. That means density goes lesser than the normal value because air expanded. Then again it come to the normal value. Then again compressed. Again it goes to 0. Again goes to normal like this. You see, rarefied. So this is density variation with respect to time. This is longitudinal wave representation. Longitudinal wave representation. This is transverse wave representation. I told you very clearly, here displacement directly you can mark in transverse wave. Displacement of the particle is perpendicular. But in longitudinal wave, particle is displacing in the same direction. So that we cannot show in y-axis. So density variation will come that we are showing in y-axis.
I mean, so in transverse and longitudinal waves.
That's what, see, look at the axis. A graph is not looking at the shape. Graph is always reading, looking at the coordinates given. See, displacement with respect to time. This is density with respect to time. Clear?
Yes, sir.
Here displacement varies, here density varies.
Okay, sir.
So looking at the shape, we cannot say these graphs are same. You have to read the graph, not look at the graph. Always remember, you have to read the graph. This is displacement. Okay, here displacement from mean position plotted. This density with respect to time is plotted. This is longitudinal wave only. Yeah? Longitudinal wave. So again, same way, here to here, 1 lambda. Here to here, 1 lambda. One compression to another compression, or one rarefaction to another rarefaction, 1 lambda. Is it over?
Yes,
Yes,
sir.
sir.
Next one, expression for progressive wave. Expression for progressive wave. Yesterday I gave the note, harmonic wave functions, we have written the note. A wave function which can be described
Yes.
through trigonometric functions like sine and cosine wave are called simple harmonic wave functions that we discussed yesterday, right?
Yes, sir.
Now this is very, very important. Expression for progressive wave. Expression for progressive wave. Okay. Now working column, you just write one thing. Look here. This is also a previous knowledge we have to choose. This is one wavelength. Say for example, wavelength lambda is 8 meter. This made one vibration, wavelength reached up here around 8 meter. Now this is 8 meter. Here it is 6 meter, 3 by 4. This is 3 meter, lambda by 2. This is lambda by 4.
It should be 4.
This is 4 meter. This is 2 meter, isn't it?
Yes,
Did you
sir.
understand that?
Sir.
Yes, sir.
Yes.
So here phase difference. This particle completed 2 pi phase. This is 0 phase. So when lambda path is completing, lambda distance it travel, 2 pi phase difference come. When 2 pi phase difference, lambda meter, that energy travel. Unit phase, okay? Write this. Unit phase lambda by 2 pi. Okay, for a distance of x. For a distance of x, we can say phi is equal to lambda by 2 pi into x. It just reverses, sorry. 1 minute. Reverse. Lambda distance when it travel, 2 pi phase. 1 meter it travel, 2 pi by lambda is a phase. When it travel, x meter, phase is equal to 2 pi by lambda into x. This is a phi. For example, here 2 meter travel, here phase 90. Let us see with the formula. Phi is equal to 2 into 180 divided by 8 in this example. 8 into x, 2 meter. Calculate. This is 4. This is 2. See, 90. It's 90. Like that, any position. Here, if you want 1 meter, you substitute. Phi is equal to 2 into 180 by 8 into 1. You will get 45 degree. Here, phase is 45 degree. Like that, any distance along x-axis when you travel, their particle is in which state of vibration you can calculate. That is the importance of this working column formulas. Is it clear?
Yes, sir.
Yes.
Now let us come back to here. Expression for progressive wave. Okay, look here. Here, draw this diagram. Here I am marking a progressive wave. Okay, it's a progressive wave. Just now we studied when the first particle making 360 vibration. Okay, this particle 0, right? Vibration.
Yes, sir.
In this, for example, one wave only will do. Yeah, this particle 0. This particle how much? Phase
90.
270. Phase
270.
270. This is
180.
180. This is
90.
90. This is 360.
360.
So a wave is a simple harmonic motion. So we can write y is equal to a sine omega t. This is the particle, beginning particle. First particle I can say y is equal to a sine omega t because this is a simple harmonic motion. Maximum distance is going up, y is equal to a. Down is equal to y is equal to minus a. It's happening in an interval of time. So this can be represented by this formula. A is the amplitude, omega is the angular speed. That means omega is more, you can see this particle vibrate faster. A is more, it displaces more into y-axis. That's the meaning of this formula, isn't it?
Yes, sir.
So here, this phase, with respect to this, if I'm marking here, this particle, how will I represent? So here I can say 0 at a time t. That means origin. Particle is at origin. At that time, instant when I'm looking, this is 360 completed. Now look at this particle at the same time. That is why it is a distance x, xt. Same time here and here I'm observing. Here the particle making a vibration, y xt. See 0 now become x. Time, same time. Amplitude. Here also maximum particle can vibrate a. And speed sine omega t, same thing. But what is the difference between this particle and this particle? This completed 360 vibration, but this completed only 270 vibration, isn't it?
Yes, sir.
Yes, sir.
That means with respect to this, minus 90 degree here. Okay, minus 90 we can write, isn't it? Phase. Am I right?
Sir, because 270 and 360 difference.
Difference, phase difference.
Okay, sir.
Say, for example, I told you here 1,000 boys are in this line. I put a boundary line here. You can move here and here, to and fro. So maximum boundary line you can go, that's called amplitude. So just now you started moving. I told you yesterday this example. First person started, second person just behind, third person just behind. If you go like that, when first person completing like this person will be having just starting the movement, isn't it?
Yes, sir.
Yes, sir.
He completed one vibration. He completed only half the vibration. He is only 1/4 the vibration. He is about to start.
Yes,
So
sir.
with respect to him, 90 degree is behind. With respect to him, 180 degrees behind. With respect to him, 270 is behind. With respect to him, 360 is behind. Isn't it?
Yes, sir.
Yes.
So when we come towards positive x-axis, phase is decreasing, right?
Yes, sir.
Yes, sir.
So here we can write the formula sine omega t minus phi. Once you get it, it's easy. This much only in this derivation. How this formula obtained. Y xt is equal to a sine omega t minus phi. Once you got it, your derivation over. Look, y xt is equal to a sine. Omega means what? 2 pi by t. 2 pi by t into t minus phi already we have written. Through a distance x when you travel, phase difference come 2 pi by lambda into x. In the working column just now I gave you, isn't it?
Yes, sir.
Finished. Y xt is equal to a sine. Now 2 pi by lambda, I'm going to take it outside. 2 pi by lambda. Okay? This lambda, 2 pi by lambda, I'm taking outside. So you'll have an objection because here lambda is not there. First term. Isn't it?
Sir.
So I'll put
Sir.
a lambda on top, lambda by t. No problem right now.
Yes, sir. No problem.
So
Minus
why-
x. Isn't it? Tell me.
Yes, sir.
No, sir.
Now y xt is equal to a sine 2 pi by lambda. 1 by t is what? Frequency. So f lambda or nu lambda we can say. 1 by t frequency. F lambda into t minus x. What is f lambda or frequency into lambda?
Velocity of wave.
Velocity.
Velocity.
Yeah. So y xt is equal to a sine 2 pi by lambda vt. This become vt minus x. This is the expression for a wave traveling in positive x-axis. If it is negative x-axis, minus of minus x will come. So plus x you have to write. So right up to here. Right down. Let us consider a progressive wave. Let us consider a progressive wave as shown in figure. Let us consider a progressive wave as shown in figure. Let the displacement of the particle, let the displacement of the particle in the medium, let the displacement of the particle in the medium in the medium. Let the displacement of the particle in the medium. At an instant t, at a distance x, from the origin can be written as, write this. So this you have written with respect to this. So this you should understand, but with respect to this you are writing. At a distance x can be written as yxt a sine omega t minus phi. A sine omega t minus phi. Here A is amplitude. Amplitude means that line you have made here. Maximum, there only all particle can go. A is amplitude. Omega is angular frequency. Omega is angular frequency. And phi is a phase difference at that instant with respect to the particle at the origin. Phi is a phase difference. Phi is a phase difference.
Omega
Is angular.
Omega is the
Angular velocity or angular frequency. Anything about angular frequency. Angular frequency increasing, this vibration become faster. Omega is angular frequency. Phi is a phase difference of that particle. Phi is the phase difference of the particle at that instant. Phi is the phase difference of the particle at that instant. Next instant it will change. Phi is the phase difference of the particle at that instant with respect to particle at origin. And substitute for omega. Yxt a sine omega is 2 pi by t into t, and phi is 2 pi by lambda into x. Then 2 pi by lambda take outside. So this lambda, for this I put 1 lambda onto the numerator, and 1 by t is frequency. Okay, so frequency into lambda, velocity. Right. This is the expression for the wave. This is the expression for the progressive wave. This is the expression for the progressive wave traveling along positive x-axis. Traveling along positive x-axis. This is the expression for the wave traveling along positive x-axis. If the wave travel in negative x-axis, then formula become what? Yxt is equal to a sine 2 pi by lambda Vt minus of minus x. That means
Plus x.
Okay, right. In general,
can you say from this is the expression for
this is expression for the progressive wave traveling in positive x-axis. This one. Then if the wave travel in negative x-axis, yxt is equal to a sine 2 pi by lambda Vt plus x. In general, the progressive wave is represented by the equation yxt is equal to a sine 2 pi by lambda Vt plus or minus x. See, today after the class, can you come one period? Then we will finish the portion today. Only 2 more derivations.
what time, sir?
Just after the class, 1:30 or 2 o'clock, something like that.
Sir, 120.
Because
Sir, wait.
the time to explain. That's a problem. Simple harmonic motion. one more thing we had to study there. Okay, this is not completed in working column, you write. Okay, look here. We studied this geometrical interpretation this way. From here only all this formula developed. And here, you see, this is the amplitude A or radius A. This is the projection. The moment of this projection only we are studying as y. So here waves, every particle of the wave also traveling this way. This is, we know, omega t. This is also omega t. From here only until now you started observing. Okay, from this point, origin of the wave. Now look, if suppose you are starting little early, late from here, little early from here, A. This is P. That means from A you started observing the particle. This point. That means now if you are taking projection and calculating y value, you are calculating y from this point to this point, right? That's wrong. Y value always measuring from origin. So this much extra phase, this is called phi naught. This is called initial phase or initial epoch. Already phase difference between the particle we studied, right? With respect to this 90 degree like that. But if you start observing from here to here, see this additional phase you are reading there. So that should not happen. That should be subtracted. Okay. So for that, the formula can be written as, look here now. This is phi naught. So we need only this much portion. Okay. Because this is equal to this. We need from here. Then only y value will come. Isn't it? So if I'm taking this as phi, look here, this is omega t now. Because I'm observing from here to here. So from here to here time I consumed. So this one is omega t. Okay, this is phi naught. Then what will be this side?
Omega t minus phi naught.
Yes, this point will be omega t minus phi naught. Therefore, how much will be this? This one.
Same, right? It will
Same.
be equal to
Same,
omega
right.
t minus phi naught.
Copy it. Omega t minus phi naught. Now your formula for y is equal to a sine omega t. We can write minus phi naught. Okay. This is initial epoch. Initial epoch, phi naught. So if initial epoch comes, that's starting from from the origin. If we started observing that oscillation before the origin, such case that extra value should be subtracted from phase. Okay, finish it fast. Draw the faster. Otherwise it will be time up only 5 minutes. Just put in working column because that we have to bring to this formula.
So what is the initial?
Initial epoch, initial phase or initial epoch. That means normally this formula we developed between phase difference between this particle and this particle. But if you start observing from here, that additional phase will come here. That should be subtracted. Is it over?
No, sir. Wait.
So today it's good strength. Please join everyone. Okay. 60. Today it was 70 students. See. But someone left in between. Okay, now look, same thing we are showing. This is same manner, but it started late. We started observing little late. For example, instead of starting from here, we started from here. So that should be added there. Then only correct phase difference will come. Isn't it? That means from here we are starting. Your A, point A from here. Look here. From this point you start observing. Okay. Then omega t is. Now this is omega t. This is omega t now. Here there is a phase little late. This from A you are starting. Now here total is omega t plus phi, right? So this omega t plus phi, isn't it?
Yes, sir.
So that will be added here now. So if you are starting late, that extra phi naught should be added here. So in general, we can write y is equal to a sine omega t plus or minus phi naught. So here also we can add it, plus or minus phi naught. This is called initial epoch, that phi naught. Next, only just two derivations, stationary wave and beats. Then your portion is over. This stationary waves concept is very interesting. Because of that concept, only we can, after studying that, only we can know in Bohr atom model, electrons when rotating, it's not losing energy. Even Earth, the planets, all moving around the sun, but they are still not losing energy. Why they are not losing energy? That idea we are getting from this stationary waves only. Once you involved in physics, you will surprise of thinking how this universe is being controlled by these kind of powers. But that involvement and interest should come, that now you are in that age. It's over.
Yes, sir.
So you have written no this formula in general. Here you have written this one. So this is initial epoch. If initial epoch is not there, this you can put 0. And if it's negative axis, instead of plus, minus you have to write. Sorry, plus you have to write. If it's moving positive axis, minus you have to write. Like that, from this formula, you should be able to choose according to the requirement. If question wave traveling in positive x direction means a sine 2 pi by lambda vt minus x. And if there is a phase lag, phi naught, then phi lag should be added. Phase lead, initial epoch, then that should be subtracted. So depends on that formula, you have to choose from this. There's a general formula. Is it clear?
Yes, sir.
Next heading, standing wave or stationary wave. Stationary wave or standing wave. Stationary wave or standing wave. Just now we studied wave progressing continuously, but this wave will not move. It will remain in the same place and the particle keep vibrating there. Wave will not advance. Energy will not advance. This is called stationary wave and standing wave. Only if energy is propagating, wave is traveling through media, only energy will be dissipating and amplitude will reduce. Amplitude reducing means, say, for example, one wave came here. Next wave, we expect damped oscillation we studied, right? Same amplitude, same length. But same length will be there, but amplitude will decrease because of energy loss. That's a damped oscillation. Clear? But if it's not traveling, there is no energy loss. It will keep remaining in the same energy vibration. These kind of waves are known as standing waves. Actually, in dual nature, we'll study. In chemistry, might have studied this Earth and all while moving along the orbit, they move in the form. Let us see this medium. Okay, look here. This is a particle. In this medium, first wave goes this way. Look here, it's progressive wave. This progressive wave is y is equal to a sine 2 pi by lambda minus vt minus x, right? It's going towards positive x-axis, you see? It's going towards positive x-axis. Suppose if it is stopping here, this wave will come back. This is a reflected wave. Okay? See, now this is going to negative x-axis. So vt plus x will come here, isn't it? Negative x-axis. See? So onward wave and reverse wave, when they come back, some places they are adding up. See? The wave which is going to this side will pull the particle upward. Same way, this also will go in the same direction. Such cases, they will be added up. These places we call node, antinode. But this places, the wave going forward wave coming back, both are vibrating opposite, so they get cancelled. Such cases, no vibration. This is called node. That means this point to this point, energy. See, in between energy is there, but one segment to other segment, energy cannot transfer. Because I told you, for transferring energy, particles should vibrate. They transfer energy, come back, receive energy, keep transferring. But all these point of nodes, particles are not vibrating. That means energy is blocked there. These kind of waves where energy cannot move forward or progress is known as stationary wave. Okay, right now. So when two sets of, right, this is one set is going forward, one set is coming back, right? When two sets of progressive waves, is antinode. When two sets of progressive wave of same type, two sets of progressive wave of same type, either both longitudinal, because one longitudinal, one transverse we cannot use, even both longitudinal or both transverse, having same amplitude. Why do they need same amplitude? When they're adding up, it will be double. When they come opposite, it should completely cancel out. Then only they should have same amplitude, because one wave pulling the particle to vibrate, say 2 centimeter up. Reverse wave pulling the wave to transfer 2 centimeter down. So these two effects get cancelled. If one is little more, there is a resultant displacement will take place. Okay, repeating. When two sets of progressive waves of same type, either both longitudinal or both transverse, having same amplitude and same time period, traveling with the same speed, along a straight path, both transverse having same amplitude or same time period, traveling with the same speed, along a straight path, but in opposite direction, are superimposed. A new set of waves are formed in which energy is not transferred.
So after the form,
But in opposite direction are superimposed. A new set of waves are formed in which energy is not transferred. These waves are known as standing waves. Next line. Let us consider a progressive wave. Am I audible?
yes,
Yes, sir.
Let us consider a progressive wave. This one, I'm talking about the first one. Let us consider a progressive wave traveling. Let us consider progressive wave traveling along positive x-axis. That is between x is equal to 0 to x is equal to L. That is between x is equal to 0 to x is equal to L. Then the displacement for the progressive wave, displacement for this progressive wave displacement for this progressive wave can be written as y1 is equal to, instead of a sine, I'm writing here r. Okay, r. Formula I'm using r because a again I'm going to use later on. R sine, usually you are using a sine, here I'm using r sine. R sine, or you can use small letter A, no problem. Otherwise you'll confuse. A sine 2 pi by lambda Vt minus x. A sine 2 pi by lambda Vt minus x, where A is amplitude of the wave. A is amplitude of the wave. That means maximum vibration of the wave is A. A is amplitude of the wave. Lambda is wavelength. V is velocity. V is velocity.
So what is A?
Amplitude.
Okay.
Lambda wavelength. V is velocity. Okay, at the point x is equal to L, this point, what happened to this wave? It's coming back, reflecting back, isn't it? At the point
Yes,
happening
sir.
back, at the point x is equal to L, the wave is reflected and traveling back. Reflected and traveling back from x is equal to L to x is equal to 0. With an additional phase of pi. With an additional phase of pi.
It is turned back.
What's the meaning of additional phase of pi? Look here. If this wave is continuing, phase is 0, it's continuing. But if this is coming back, say 180 degrees, suppose you are swimming here, okay? You are swimming here. After touching here, suppose you are coming back. After touching here, you are coming back. How many degree you turn now?
180.
180. That
180.
additional phase that we are taking here. Because in a small instant of time, there's a lag happening. So here I told you, if there's a lag, that should be subtracted. If it is continuing, okay, phase is continuing. But here, the time that reversing time taking place. Clear? So that should be additional phase. That should be subtracted here. That is called initial epoch. You remember we studied initial epoch. Continue. So at the point x is equal to L, the wave is reflected back and traveling from x is equal to L to x is equal to 0 with an additional phase of pi. With an additional phase of pi. Then this reflected wave can be written as y2 is equal to a sine 2 pi by lambda Vt plus x. See, it's coming towards back. So plus x and plus pi. That additional phase we have to add here. Plus pi. If it's lagging, we have to add. If it's ahead, we have to subtract. Pi. Sine theta plus pi is equal to minus sine theta. That means this one. This is theta. Up to here is theta plus pi. Okay. So we can write here y2 is equal to minus a sine 2 pi by lambda Vt plus x. Now this pi is not there. That's why minus sign I put here. If you want, you can write here sine theta plus pi minus sine theta. Now by superposition principle, when these waves added, see some places they are adding like that. When this added by superposition principle. Superposition principle means when we are meeting at a point, there will be vector addition. Waves will be added up. By superposition principle, by superposition principle, when they are added, It's a vector addition. When they are added, y is equal to y1 plus y2. Y is equal to y1 plus y2. Y is equal to y1 plus y2. Then substitute for y1 and y2. Y is equal to, what is y? R sine 2 pi by lambda.
Sir, A, right? A sign.
A sine 2 pi by lambda Vt minus x minus A sine 2 pi by lambda Vt plus x. Then here we have to use the formula sine A minus sine B. You study this formula, right? Sine A minus sine B. That's equal to 2 cos A plus B by 2. A plus B by 2 into sine A minus B by 2. A minus B by 2 into sine A minus B by 2. Here A means this one. This part is called A. This is B. So first working column you can do later. A plus B by 2. Vt minus x plus Vt plus x by 2. Then A minus B by 2. Then substitute. Then final answer will come like this. Y is equal to, after substituting, your answer will come A 2 cos 2 pi Vt by lambda. 2 pi by lambda into Vt into sine 2 pi by lambda into x. Like this you will get. After substituting this formula will be like this. So this 2A is the total amplitude, A plus A, maximum amplitude. That means this region. Okay. So y is equal to 2A. This cos, this value keep changing. You see, here when they are adding maximum, here they are reducing 0. Again, their amplitude is increasing to maximum, again decreasing. That means the whole thing is changing. That amplitude of variation is changing here. See, this whole thing keep changing. That means 2A come only one time, then 0, then become 2A, then become 0. That amplitude keep changing. Clear? So we can write here 2A cos omega t, 2A cos 2 pi by lambda Vt. This much portion we can take as A. Okay, it's a varying amplitude. So y is equal to A sine 2 pi by lambda into x. This is the expression for stationary wave. Here A is equal to 2A cos 2 pi by lambda. 2A cos 2 pi by lambda Vt. This is A. Okay. Clear?
Yes.
So this position when particles of two waves adding, this much only amplitude is coming. Here this much, here maximum, here again decreasing. That's because of phase decreasing. Is it over?
Yes, sir.
Now look,
Yes, sir.
different modes of vibration. Last topic, different modes of vibration.
Sir, beats is not coming.
Which one?
Beats.
Beats also, I think today you will not have time beats. One more class I need. If you can give me this week, I can finish it. Then Sunday onwards, you are free. Otherwise, anytime next one more period I need beats.
So you can take one period in vacation.
Yes, like that. But we cannot declare it's finished. That's a problem. Because of just one derivation.
Sir, Sunday after exam, you can keep.
Sunday after exam, if you come, I'll just finish one period enough. Different modes of vibration. This is different modes of vibration. Look here. First one, vibration in a stretched string. Vibration in a stretched string. This portion syllabus they have shown, but in a deleted syllabus it is marked. So that we'll see later. Now I'll teach you anyway. Vibration in a stretched string. It's very easy. It's not complicated. Look here. If you take a string like that, for example, just think of a guitar string. Okay, you are tightening it both ends. Exactly middle, if you strike, you will hear high frequency, a low frequency, broadest sound. That means middle, if you vibrate, I will tell you first thing. How can you recognize high frequency and low frequency? Male voice, vocal cord is vibrating less number of times. So that is producing bigger waves. In 1 second, less number of times only it's vibrating. So large size waves will come. These kind of waves, when falling into a eardrum, sound is bigger, louder. So not louder, broader. Male voice. But female voice, their vocal cord vibrating very, very fast. That's what very sharp frequency is penetrating. Then drum. If you beat on the drum, it's producing low frequency. But guitar string, high frequency. So in this guitar string itself, different types of frequency we can produce. For example, exactly in the middle, if you strike, frequency is less. I will show you how. Then you will hear a sound like tung, one sound will come. But if you go to 1/4, if you strike, ting, it will go like this. Is it clear? So tung, like that, very big sound, then ting, it will go suddenly down. So this is a frequency variation happens. Okay, that means different side if you strike. That's what guitarists and all, they are vibrating at different places to produce different frequencies. Is it clear?
Yes, sir.
So what are the possible frequencies here? The minimum one, look here, the minimum. Middle, if you vibrate, this will vibrate like this. You see, only one wave can accommodate in this length. L is the length. Okay. Now you see, in a stationary wave, ear to ear lambda by 2. That means node to node lambda by 2. And node to antinode, if you are taking lambda by 4. See, this is lambda by 4. So what will be this distance? Lambda by 2, right?
Yes. Sir.
Sir.
So here we can say lambda is equal to 2L. But we know frequency is equal to V by lambda. V is equal to F lambda. Frequency is equal to V by lambda. So F is equal to V divided by 2L. So this is the minimum frequency on a string we can produce. Then what is the next frequency possible? Let us see. Next frequency. If you're vibrating exactly 1/4, see, this will vibrate like this portion and wave will continue here, you see. Now one lambda form, right? Lambda by 2, lambda by 2, L is equal to lambda. Now you see, lambda is twice lambda by 2. So we can say here, F is equal to V by lambda. Okay, this is F1. F2. V divided by lambda is now L. Now we want to compare with this. Numerator and denominator multiply by 2. Okay. Then we can get, see, 2 I'm multiplying. That means this frequency is 2 times this, right?
Yes, sir.
So frequency doubled. So the F2 is 2F1. Here numerator and denominator I multiply by 2 in order to get this formula twice this. Okay, see, V by 2L. Twice of that is V by L actually. Isn't it?
Yes, sir.
So that is 2F1. Now third case. Next segment. See this much. 1, 2, 3 will form. In between no waves can form. See here same length. But again 1/8 if you vibrate, it will go to 3. See, like this it will go. 3 segments. So lambda by 2, lambda by 2, lambda by 2. So L is equal to 3/2 lambda and lambda is equal to 2L by 3. Then here F3 is equal to V by 2L by 3. Then F3 is equal to 3 of F1. Clear? Like that, if you're taking N, finally Fn can be NF1. First one is known as fundamental note. Fundamental note. First harmonic. Musicians and all, they're saying note. In physics, we call first harmonic. First
Sir,
harmonic.
it's written fundamental frequency here in the notes.
I'm going to, this is fundamental note. I'll tell you that. Fundamental note. First one we can write, what is this? Fundamental note. Usually musicians use the term note. Then fundamental frequency. Fundamental frequency. And also first harmonic. First harmonic. In the second case, second harmonic. But first overtone. This is called overtone. See, tone, one extra coming, overtone. This is second overtone. Third harmonic. But second overtone. This is the way it is classified. Nth harmonic, but n-1th overtone.
Sir, what's the first one?
Fundamental note, fundamental frequency, first harmonic. Second one, second harmonic. Third one, third harmonic. Nth one, nth harmonic. But overtone, first is not actually not overtone. Second only we call first overtone. Third, second overtone. Fourth, third overtone. Like that. That's what I said. Nth harmonic, n-1th overtone. Is it clear? Is it over?
No, sir, just a...
Finished. Can I continue?
Yes, sir. Yes, sir.
Now, next one, vibrations in one end open pipe. Vibrations in one end open pipe. It's also known as organ pipes. If possible, in YouTube, see these animations. One end open pipe. Look here. Here, longitudinal waves only. See, air is there, longitudinal wave. From here, if you blow, like this, you blow into a pipe, then this air will get compressed. Okay, that compression is equal to which one? Node. Then from there, it gets reflected back. That means graphically, I can show this. When you just blow into it, air will get compressed. At the lowest point, they get maximum compression like this, and they get reflected back. So here we can say density maximum, here density less. Like this, only stationary waves are forming in what? Pipes. This is longitudinal wave, not transverse wave. This shows density variation only. Now this is, see, if you're comparing with the longitudinal wave graph, here to here, see this open pipe always, this only will form at this end. And here it forms down. So this is lambda by 4, see 1/4 of lambda. So here L is equal to lambda by 4. Lambda is equal to 4L. Frequency F1 is equal to V by 4L. This is fundamental frequency, fundamental note. Clear? Now, see the second one. Same tube, little more force I'm giving in blowing. Then in between, air get compressed, expand, and again compressed, again expand, again compress and come out. That means this way. These two portions. See, after this will form. Like this, you see. This air here get compressed, then expand, again compressed, again expand, compress and come out. Like this. Because always this antinode will come at the free end. In the case of string, this is starting point, always node only will come here, this to end. Clear? So this one now, lambda by 2, isn't it? Here to here, lambda by 2. This is lambda by 4. So total length is equal to 3 by 4 lambda. So F2 is equal to V divided by 4L by 3. 4L by 3. That means 3F1. So here no second harmonic, directly third harmonic only we are getting. But first overtone. Okay, next one. Little more. Strongly if you blow, it will come like this. See? It will form like this. See? 1, 2, third one. Like this. So lambda by 4, lambda by 4, sorry, lambda by 2, lambda by 2, lambda by 4. So 1/4, 5 by 4 lambda, right? 1/4 means is equal to L. So lambda is equal to 4L by 5. Then F3 is equal to V divided by 4L by 5. So 5F1, you see? So F1, 3F1, 5F1, 7F1, 2N plus F1. Like that. Fn is equal to 2N plus 1 F1. N is equal to 0, 1, 2, 3 and so on. If N is equal to 0, first one you take here. 0. Sorry, 1, 2, 3 you take. That's better. Fn is equal to 2N minus 1 F1. N is equal to 1, 2, 3 and so on. When N is 1, this is 2. 2 minus 1, 1. 1 F1. See, first one. 2 you substitute, you will get 3 F1. 3 you substitute, you will get 4 F1. So this is fundamental note. Fundamental note. First harmonic or fundamental frequency. This is first overtone. First overtone. Okay. But third harmonic. Third harmonic. Look at this 3. Third harmonic. This is second overtone. But fifth harmonic. Here no second and fourth harmonic. All odd harmonics will come. Now here 1, 2 and open pipe. 2 and open pipe. This is now mainly using in music instruments and all. This idea. Look, if you blow, it will compress and go to other side. It won't reflect. So what happens here? This way waves will come. This way. That means both end antinodes will come. So this we know lambda by 4. This is lambda by 4. So L is equal to lambda by 2. Lambda is equal to 2L. F1 is equal to V by lambda. F1 is equal to V by 2L. See, same like in stretched string. Everything will repeat like in stretched string. lambda by 2, lambda by 2, lambda by 4, lambda by 4. So this is 1, 1.5. 3 by 2 lambda is equal to L. Lambda is equal to 2L by 3. Okay. Then F2 is equal to V by 2L by 3. There is mistake. 3 by 2 means 1.5, right? This is correct, right? 1, 1.5. 3 by 2, lambda is equal to L. So lambda is equal to 2L by 3. What is that mistake happening? This is V by 2L, right? Correct. Stretched string, have you got? In stretched string? 2L by 3, correct. Here one extra I did. That's a problem. Sorry. Think like this. First these two got, now this source will come. Okay, like this. Like this only will come. No, that's why. Lambda by 4, lambda by 2, lambda by 4. I went to the next stage. Then this is 1 lambda, say equal to L, isn't it? See, lambda by 4, lambda by 4, lambda by 2 plus lambda by 2, 1 lambda. So F2 is equal to V by lambda. F2 is equal to V by L. So F2 is equal to numerator and denominator multiply by 2. That means 2F1. Then third one like this. So the third one you can draw now yourself. See F2 here. It will come 3F1, isn't it? Lambda by 2, lambda by 2, lambda by 4, lambda by 4. So L is equal to 3 by 2 lambda. Okay, so lambda is equal to 2L by 3. So F3 is equal to V by lambda. F3 is equal to V divided by 2L by 3. So 3F1. Same like in structured string. So this is about. Now beats, if you want just an introduction, I'll give you. I think notes you can follow that after that. Okay, just 5 minutes if you give me, I can finish beats idea. And if you want, we'll repeat again. Is it over?
Yes, sir.
No, sir.
Get an idea, you can just read the note and see. It's only derivation, just mathematical derivation.
Sir, done.
Now look, beats. Okay, beats animation I'll send you, you listen to that, okay? Look, this idea, here waves are coming back, right? Going back and coming back and adding up. But in beats, they are going in one direction, okay? Look here. This is the last graph. Suppose this is, you can draw diagram of beats. Analytical approach of beats. I'm dividing this into 4. Say 4 equal spacing. 1, 2, 3, oh, it became 5. I'm dividing into 4 equal spacing. 1, 2, 3, 4. Yeah. 1, 2, 3, 4. And here I'm marking a wave. Look here. This is the wave. 2 waves I'm accommodating in one segment. Okay. Look here. Here, 1 wave, again 1 wave. So 2, 1 wave, second wave. 4, 1 wave, second wave. 6, 1 wave, second wave. So total 8 hertz, this frequency. From this source producing 8 hertz, imagine. Now I'm taking another source. Okay, another source. Same length. Okay, they are traveling in same direction. This I'm going to divide into same 4 segment. hertz. But here 6 hertz only I have to accommodate. Here I'm going to accommodate only 6 hertz. Okay, look here. Then 1.5 only will fit into 1.5. See? Next to 1.5. Again, next to 1.5. Again, next to 1.5. See? This little bigger wave. 6 hertz. Total 6 hertz. Now you see at the initial point, crust and crust are adding. So 2 particles going in same direction are adding. Suppose here one simple pendulum going to 1 centimeter and here, another one exactly coming and hitting with the same force, it will go to 2. While coming back also it will go to 2. Isn't it? Suppose a simple pendulum is moving, you're pushing in the direction of motion, it's going to 2. So while coming back, one side 1, one side 2, it will not go like that. Other side also it will go to same distance again, isn't it? Am I right?
Yes, sir.
So this particle, when they are meeting, they will add up. They will add up. Suppose this is 1 centimeter, 1 centimeter. That will start moving 2 centimeter up, 2 centimeter down, 2 centimeter up, 2 centimeter up. So these are all keep moving up and down. All waves are each particle moving up and down. So this region, their motion will be doubled up. So that I'm going to show here. And this region is this region. They are coming opposite. This is coming down. This is going up. They got cancelled. And this region they are adding up. This region they are cancelling out. Here they are adding up. So like that 2 region will come. Let us see that now. Okay. This is the resultant wave is forming now. Light color I'm using that. Yeah. I'm going to fill in this gap. Okay, look here. These 2 first will add up. So that is maximum. Yes, sir, reverse it should come. Here maximum amplitude. First I will mark. These 2 will add up here. So this point maximum amplitude will come vibration. But these 2 point it cancel out. 0 amplitude. These 2 point it will add up. See, both are in same direction. So maximum amplitude. This point you see they are cancelling out. So 0. This point they are adding up. So maximum amplitude of vibration. So wave will be like this. Like this it will come. That means, see, total frequency will be 6 plus 8, 15. It will be added like that. But amplitude we are discussing here. Now what will happen? This point you will hear a louder sound, high sound, peak, one sound. Suddenly it will stop. Again, peak, stop, peak, stop, like that. So this number of sounds heard depends on difference in frequency. In this case, in 1 second, 2 times you will hear. That means in guitar string and all, 2 strings you just strike. Then listen carefully. They will have slight difference in frequency. Then you will hear a sound like like that. One sound will come up and down. So musicians, they know how many sounds will give them correct tuning. And this is using in mines. In mines, if they want to check whether poisonous gas is there, we cannot go down and check. So what they do, first they take a sample of pure air and send a vibration with a tuning fork. So that beats they study. And they send it to the mine. They know if methane may be there. Methane is poisonous. If methane content is more, methane and air will vibrate different way. So number of beats listening to, they will know how much part of methane contained in it. So these are all the main studies going on in these beats. Is it clear? So this is called graphical analysis. So just write the definition of beats. When 2 sound waves of slightly different frequencies. When 2 sound waves of slightly different frequencies. Bracket not less than, not more than 10 hertz. That reason I'll tell you later. Not more than 10 hertz. Bracket. the difference should not be 20 and 50 like that. It should be only, difference should be less than 10. Because our audibility is 0.1 second. Anything you hear, 0.1 second, that will retain in your brain. Next, your brain will accept only after 0.1. So in 1 second, 10 means just a break between two beats coming 0.1. So here very clearly see 0.5, 0.5 gap is coming for one high beat, low beat, high beat, low beat like that. So clearly can hear it. That's what I said, not more than 10 hertz bracket. Continue. When two sound waves of slightly different frequencies, bracket not more than 10 hertz, traveling in a medium, along the same direction, are superimposed on each other, then intensity of resultant wave superimposed on each other, then intensity of the resultant wave at a particular position, rises and falls regularly with the time. This phenomenon rises and falls regularly with the time. This phenomenon of regular variation of intensity of sound. This phenomenon of regular variation of intensity of sound. This regular variation of intensity of sound with respect to time. When two waves of nearly equal frequencies.
Sir, regular variation of intensity of.
This phenomenon of regular variation of intensity of two waves with respect to time. When two sound waves of nearly equal frequencies superimposed on each other are called beats. Then analytical treatment of beats, this graph.
Are called
Beats. And one more sentence. One beat is said to be found. One beat is said to be formed. One beat is said to be formed when intensity become maximum. Again, intensity become maximum. Again, after becoming minimum in between. It's there in the note. Easy. This point to this point, high pitch, low pitch, high pitch, one beat. High pitch, low pitch, high pitch, second beat. Total 2 beats. This is the meaning. Okay. And this graph, graphical treatment of beats. This one. Okay. We take a screenshot, or I have given in the note. Analytical treatment of beats that you can read. Same like in stationary wave, same formulas they are using. Just go through it. If you have any doubt, after the class, I can just help you. That final formula. But all other derivation, everything I have written there. You see, formula which you used, everything is written here. This formula they used here. Clear? Maybe last 1 or 2 steps you may not understand. Go through it. After exam, if you don't understand, tell me. We will have a class. Otherwise, I will go with revision. Today, I am declaring portion over. Okay?
Sir, what about
I'll post in the
Doppler
group.
effect?
Sir.
Okay.
Doppler effect not there. It's cancelled.
Okay, sir.
So your physics portion of 11th over. Now 2 chapters. From where we went faster? Can you tell me?
Gravity.
From gravitation.
Gravitation.
Yes, sir.
Gravity from the beginning.
Yes, sir.
But problem solve we did thoroughly. All problems we did, right?
Yes, sir. Just the theory.
Now again, if you want gravitation, if you want, anyway, it's a revision. Gravitation, I will give notes and we'll go completely in systematic from Sunday onwards. So after
Okay,
the
sir.
class, you come to 1 hour, you take rest after the class and come to me.